When astronomers finished designing the James Webb Space Telescope, they had a very specific idea of what it was going to find. They had models, they had simulations, they had decades of observations from Hubble and other telescopes pointing in the same direction. The early universe, according to everything they understood, should have looked a certain way. Small galaxies, faint ones, chaotic, unformed structures just beginning to pull themselves together out of primordial gas. That was the prediction. That was what the science said should be out there, and Webb was going to go find it and confirm it. That is not what happened. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. What Webb found instead were galaxies that had no business existing. Massive, luminous, surprisingly well-structured systems sitting in a universe that was only a few 100 million years old. A universe that had barely started. The Big Bang happened 13.8 billion years ago. These galaxies were already shining just 300, 400, 500 million years after that. Think about what that means. The universe at that age was roughly 2 to 3% of its current age. It was an infant. It had no heavy elements to speak of. It had no generations of stars that had lived and died and scattered enriched material back into space. It had almost nothing to work with. And yet there they were, enormous, bright, fully formed, sitting in the data like something that should not be possible. Astronomers did what scientists always do when they get a result they don't expect. They checked the instruments. They checked the calibration. They ran the numbers again. They had other teams look at the same data, and the galaxies kept coming back, not as errors, not as artifacts of some new telescope still being calibrated, as real objects confirmed through spectroscopy, confirmed through multiple independent methods, confirmed as existing at the very edge of what we can observe. Here is what makes this genuinely unsettling, and not just surprising. The standard model of cosmology is not a rough sketch. It is a precise, mathematically rigorous framework that has been tested against observation after observation for decades. It successfully predicted the structure of the cosmic microwave background. It predicted the large-scale distribution of galaxies we see across the universe today. It predicted the abundance of hydrogen and helium left over from the Big Bang. It has an extraordinary track record. When a model like that starts producing predictions that don't match what you're seeing, you don't just shrug. You start asking whether something is fundamentally wrong. And Webb is not producing one or two anomalies. It is producing them by the hundreds. Galaxies too massive for their age. Galaxies too bright for the number of stars they should contain. Galaxies with structures that should require hundreds of millions of years to form, existing at times when that kind of time simply wasn't available. The numbers don't add up. They don't add up in ways that are hard to explain away with small adjustments to existing theory. Our brains didn't evolve to process the scales involved here. When we say a galaxy exists 300 million years after the Big Bang, that number doesn't land the way it should. 300 million years sounds long. It is not long, not in cosmic terms. The Sun alone is 4.6 billion years old. The universe is 13.8 billion years old. 300 million years after the Big Bang is the universe at less than 1/30th of its current age. There was almost no time. And somehow, in almost no time, something was already assembling structures that took the universe billions of years to produce later on. That is the problem Webb has handed cosmologists. Not a small puzzle at the edges of the data. A direct challenge to the timeline at the center of the model. By the end of this, you're going to understand exactly what the James Webb Space Telescope found out there at the edge of the observable universe. You're going to understand why it shocked the astronomers who built the thing. You're going to understand what the standard model predicted, why those predictions seemed so solid, and what it means that the observations keep refusing to cooperate. And the deeper it looked, the stranger things got. To understand why Webb's discoveries are so strange, you first have to understand what the universe is supposed to look like at its beginning. The standard model of cosmology is called Lambda-CDM. It's been the foundation of modern cosmology for decades. It explains how the universe began, how it expanded, how matter clumped together under gravity, and how galaxies eventually formed. And for decades, it worked. Every major test threw at it. It passed. It predicted the distribution of galaxies across the sky. It predicted the temperature fluctuations in the cosmic microwave background. It predicted the abundance of hydrogen and helium left over from the Big Bang. This wasn't a rough sketch of the universe. It was a precise, mathematically rigorous framework that had earned the confidence of almost every working cosmologist on the planet. So what does that model say the early universe looked like? Start at the beginning. About 13.8 billion years ago, everything that exists was compressed into a single point of unimaginable density and temperature. Then the Big Bang. In the first fraction of a second, the universe expanded faster than light, stretching space itself outward in every direction. The early universe was a dense, blindingly hot plasma of protons, neutrons, electrons, and photons, all crammed together so tightly that light couldn't travel more than a tiny distance before being absorbed and re-emitted. The universe was opaque. There was no such thing as a transparent sky. There was no such thing as a view. This went on for about 380,000 years. Then something changed. The universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. The moment that happened, the universe became transparent for the first time. Photons could travel freely through space. That ancient flash of light still exists today as the cosmic microwave background, a faint glow of radiation detectable in every direction you look. It's a photograph of the universe at 380,000 years old, and it's almost perfectly uniform, with tiny fluctuations in temperature representing slightly denser and slightly less dense regions of matter. Those tiny fluctuations are important. They're the seeds of everything that came after. But after that moment of first light came a long period of darkness. Astronomers call it the cosmic dark ages. The neutral hydrogen filled the universe like fog. There were no stars yet. There were no galaxies, just hydrogen and helium gas, slowly drifting in the dark, gradually being pulled together by gravity toward those slightly denser regions. This lasted hundreds of millions of years. Think about that. Hundreds of millions of years of darkness, with nothing visible anywhere in the universe. This dark age was crucial, a necessary waiting period before large-scale structure could emerge from near uniformity. The tiny fluctuations in the microwave background were the only seeds available for gravity to work with. Variations of just 1 part in 10,000 might seem insignificant, but they were everything. Without them, the universe would have remained perfectly uniform forever. But gravity relentlessly pulled on these subtle differences, slowly amplifying them over millions of years. The process was extraordinarily slow, operating on timescales that challenge human intuition. Denser regions gradually accumulated more matter as surrounding gas was drawn toward them. Less dense regions became even more empty as their material drained away. This cosmic tug-of-war would eventually create galaxies, but only after hundreds of millions of years of patient, invisible labor. Eventually, gravity won. The denser regions pulled in more gas. The gas collapsed into smaller clumps. Those clumps grew dense enough and hot enough to ignite nuclear fusion. The first stars switched on, and those first stars were small, scattered and embedded in tiny, irregular proto-galaxies that barely deserved the name. They weren't anything like the Milky Way. They weren't organized. They had no spiral arms, no defined structure. They were just loose, chaotic collections of young stars and gas clouds, stumbling toward each other under gravity, merging, breaking apart, slowly building up mass over enormous timescales. Here's a way to think about it. Imagine you're building a city from nothing. You don't start with skyscrapers. You start with a campsite, a few tents, a fire pit, maybe some rough shelters made from whatever's nearby. Over years, roads get built. Small buildings go up. Infrastructure develops. It takes generations before anything resembling a real city exists. The early universe, according to the model, was at the campsite stage. Tiny structures, simple ones. Nothing complex, nothing large, nothing well organized. There simply hadn't been enough time for gravity to do the work of assembling large amounts of matter into coherent structures. This prediction was very specific. Lambda-CDM said that in the first few 100 million years after the Big Bang, galaxies should be small and faint. Their stellar masses should be low, because stars take time to form, and forming a lot of them requires raw material accumulating over long periods. Their structures should be chaotic, because the mergers and interactions driving growth were still in their violent early phases. There shouldn't be anything recognizable as a mature galaxy. Nothing ordered, nothing massive. Just small, dim, irregular blobs of star-forming gas. Hubble confirmed this picture. When the Hubble Space Telescope looked at the deepest reaches of the universe it could observe, it found exactly what the model predicted. Faint smudges, irregular blobs, tiny, chaotic structures barely distinguishable from noise. The Hubble Ultra-Deep Field Image, one of the most famous astronomical photographs ever taken, showed thousands of early galaxies looking precisely like what Lambda-CDM said they should look like. Small, messy, nothing like a finished galaxy. Astronomers looked at that image and felt confirmed. The model held. Before Webb launched, astronomers ran detailed computer simulations of what the new telescope would see when it looked even deeper than Hubble. They had the model. They had the physics. They had decades of observational data feeding into those simulations. The predictions were specific. Webb would see galaxies with low stellar masses, probably less than 1 billion times the mass of the Sun. It would see faint, compact, irregular structures. It would see the early stages of galaxy assembly, chaotic and unresolved. The simulations generated synthetic images of what those faint proto-galaxies would look like in Webb's infrared detectors. Astronomers published those predictions. They were confident enough in them to write papers about what Webb was going to find before it had seen a single photon from the early universe. On Christmas Day 2021, the James Webb Space Telescope launched from French Guiana, carrying every one of those assumptions into space with it. The first deep field images came back, and astronomers started going through the data, and almost immediately the numbers didn't add up. This wasn't a subtle problem. It wasn't a small discrepancy that required careful statistical analysis to notice. The galaxies Webb was finding in the early universe were too bright, too massive, too structured, not by a small margin, by factors that made the predictions look almost laughable in retrospect. Researchers who had spent years running simulations, calculating what the telescope would find, were looking at their screens and seeing something that simply should not have been there. The models said the early universe was supposed to be full of small, faint, chaotic proto-galaxies, still in the earliest stages of assembly. What Webb sent back looked nothing like that. To understand why this was so alarming, you have to understand what astronomers mean when they say a galaxy is too massive. Every star in a galaxy has to be built from raw material. Gas collapses. Fusion ignites. Stars live out their lives, some of them exploding, seeding the surrounding space with heavier elements. New generations of stars form from that enriched gas. Each step takes time. There are real physical limits to how quickly this process can happen. You cannot compress billions of years of stellar evolution into a few 100 million years, any more than you can compress a forest into an afternoon. The models calculated these limits carefully. They set firm upper bounds on how much stellar mass could accumulate in the time available. Webb was finding galaxies that blew past those now limits. Think about it this way. Imagine someone shows you a photograph of a 100-story skyscraper and tells you construction started 3 months ago. You wouldn't question your ability to read the calendar. You'd question the photograph. That's roughly the position astronomers found themselves in. The galaxies existed when the universe was only a few 100 million years old. At that age, based on everything we understood about how structure forms, those galaxies shouldn't have had time to build the stellar mass they apparently contained. The math didn't work. Before anyone could draw conclusions, they had to figure out how old these galaxies actually were, and that requires understanding redshift. When a galaxy is moving away from us, and because the universe is expanding, every distant galaxy is moving away from us, the light it emits gets stretched. The wavelengths get longer. Longer wavelengths means the light shifts toward the red end of the spectrum. The faster the recession, the greater the stretch. The greater the stretch, the higher the redshift. And here's the key part. Because the universe has been expanding at a known rate since the Big Bang, a galaxy's redshift tells you directly how far away it is. And distance in space is the same as distance in time. A galaxy with a very high redshift is both very far away and very old. When astronomers measure a redshift of 10 or 12 or 14, they're looking at a galaxy that existed when the universe was only a few 100 million years old. They're seeing light that left that galaxy more than 13 billion years ago. The first detections of these extreme objects came through photometric imaging. Webb's cameras were capturing the galaxies in multiple wavelength bands, and from the pattern of brightness across those bands, astronomers could estimate the redshift. This is a powerful technique. It's fast. It lets you survey enormous numbers of objects quickly. But it's an estimate. There are assumptions built into it. There's room for error. And when the numbers started coming back looking impossible, the skepticism started almost immediately. Maybe the redshift estimates were off. Maybe the photometric technique was being fooled by some unusual property of these objects. Maybe there were calibration issues with the new instrument. Webb was a brand new telescope. No instrument comes out of the box perfectly characterized. The detectors had quirks. The calibration pipeline needed refinement. Several astronomers argued, reasonably, that these weren't real detections of impossibly massive early galaxies. They were artifacts. They were measurement errors. The universe was fine. The models were fine. The telescope just needed more time to be properly calibrated. That skepticism was healthy. It was exactly how science is supposed to work. Extraordinary claims require extraordinary evidence, and seeing galaxies that shouldn't exist is about as extraordinary as it gets. So astronomers started going after spectroscopic confirmation. This is a completely different process from imaging. Instead of measuring how bright an object is across several broad color bands, spectroscopy splits the light into its full spectrum, wavelength by wavelength. When you do that, you see features. Specific wavelength where the light is brighter or dimmer, corresponding to specific chemical elements in the galaxy, absorbing or emitting light at precise frequencies. These features are like fingerprints. They're sharp, they're definitive, and crucially, they shift in a predictable way based on the galaxy's redshift. If you see a known spectral feature at a wavelength that's been stretched by exactly the amount you'd expect from a galaxy at redshift 10, there's no ambiguity. You're not dealing with a broad statistical estimate anymore. You have a precise measurement. You know how far away this galaxy is. You know how old it is. The spectroscopy is the court of last resort in this kind of argument. And when the spectroscopic confirmations came back, the candidates held up. Not all of them. Some of the most extreme photometric estimates got revised downward when the spectra came in. That was expected. But a substantial number were confirmed. The redshifts were real. The galaxies were genuinely ancient, and they were genuinely too bright for what the models allowed at those epochs. The initial detections weren't noise. They weren't calibration errors. The early universe really did contain massive luminous galaxies that had no business being that large that soon. The scale of the problem became clearer as more data accumulated. These weren't isolated oddballs, a handful of weird outliers that could be explained by unusual local conditions. Webb was finding them across its deep fields. The sheer number of bright early galaxies was far higher than the simulations had predicted. Researchers began running the statistics, even being conservative about the mass estimates, even accounting for every known source of uncertainty. The population of early massive galaxies was inconsistent with the standard model. Not slightly inconsistent, deeply inconsistent. Some teams went back and re-examined their analysis pipelines from the beginning, looking for any systematic error that could explain the results. They checked the photometric calibration. They reran the spectroscopic reductions. They compared results across different observing programs, different instruments on the telescope, different teams using different software. The answers kept coming back the same. Every time they rechecked the measurements, the galaxies were still there, still too bright, still too massive, still too early. The galaxy is called month-over-month Z14, and it exists 280 million years after the Big Bang. That sentence requires a moment. Not 280 million years ago from now, from the Big Bang, from the very beginning of everything. The universe is estimated to be 13.8 billion years old. Month-over-month Z14 existed when the universe was only 280 million years into that total. That's roughly 2% of the universe's current age. Think about what that means. If the entire history of the universe were compressed into a single year, month over month, it 14 would exist on January 7th. The light we're seeing from this galaxy left it 13.5 billion years ago. It has been traveling through expanding space ever since. While that light was crossing the cosmos, the first fish appeared on Earth, then the first land animals, then the dinosaurs rose and went extinct, then mammals diversified, then a species of primate developed language and agriculture, and eventually built a space telescope. And only then, after all of that, did the light finally arrive. That's how far away month-over-month Z14 is. That's how old this signal is. The number astronomers use to express this distance is called a redshift. When the universe expands, it stretches the wavelengths of light travelling through it. The further light has travelled, the more it gets stretched. Shorter wavelengths shift toward the red end of the spectrum. The redshift value is a direct measure of how much stretching has occurred, and it maps onto both distance and time. Month-over-month Z14 has a redshift of 14.44. For context, most galaxies we observe in everyday astronomy have redshifts below 1. Hubble's deepest observations pushed into the range of 8 or 9. Month-over-month Z14 sits at 14.44. That number represents the boundary of what any telescope has ever confirmed, the furthest back in time we have ever directly seen. Finding it wasn't a single dramatic moment, it was a process. Astronomers combed through existing Webb images, searching for candidates that matched the expected signature of extremely distant objects. Distant galaxies don't look the same as nearby ones in raw images. Their light arrives stretched and faint, concentrated in infrared wavelengths our eyes can't detect. Researchers flag them based on color patterns across multiple imaging filters, looking for sources that appear in some filters and vanish completely in others. The disappearing act is the clue. Light from extremely distant galaxies gets absorbed by neutral hydrogen before it ever reaches us at certain wavelengths, which creates a distinctive dropout signature. Month-over-month, Z14 showed up as a candidate. It was bright, unusually bright, suspiciously bright for something that was supposed to be that far away. That brightness was itself a red flag of a different kind, because objects at this distance should be faint. The team, led by Rohan Naidu at MIT's Kavli Institute for Astrophysics and Space Research, flagged it and then did what astronomers always do when imaging alone isn't enough. They pointed Webb's NIR spec instrument at it. NISPEC is a spectrograph. It doesn't just collect light, it splits it. It spreads the light from a target across hundreds of individual wavelength channels, producing what's called a spectrum. A spectrum is a fingerprint. Different elements absorb and emit light at very specific wavelengths. Those patterns don't change. Hydrogen always absorbs in the same places. Carbon always emits in the same places. When you read a spectrum, you're reading the chemistry of an object directly from its light. Spectroscopic confirmation is definitive in a way that imaging simply isn't. An image can fool you, noise, calibration errors, unusual nearby objects, all of it can mimic the appearance of a distant galaxy. A spectrum can't lie in the same way. The chemical fingerprints are either there or they aren't. Webb turned NI spec toward month-over-month SED, 14 in April 2025. The results came back. The spectrum was real. The redshift was 14.44. The galaxy existed 280 million years after the Big Bang. The record was confirmed. What makes this confirmation historically significant is that it represents the culmination of decades of observational astronomy, pushing toward a fundamental horizon. Astronomers have spent generations trying to reach this far back in time, developing better instruments, refining detection methods, and gradually working their way deeper into the cosmic past. Each new generation of telescopes has approached this boundary a little more closely. Ground-based observatories gave way to Hubble, which eventually exhausted its own capabilities at these extreme distances. Webb was specifically designed to surpass those limits. Finding month-over-month Z14 means Webb is doing exactly what it was built to do, probing the universe at an age when galaxies were barely beginning to form. And then came the next problem. Month-over-month, Z14 isn't a faint smear. It isn't a diffuse, barely there whisper of ancient light. It's compact, it's bright, it has structure. This is not what a galaxy forming 280 million years after the Big Bang is supposed to look like. At that age, the universe wasn't finished clearing the fog. Neutral hydrogen from the Big Bang still blanketed enormous regions of space, absorbing ultraviolet light and making the cosmos opaque in ways it no longer is today. Early galaxies were supposed to be struggling against that fog, small and faint and scattered, slowly building up their first generations of stars. Month-over-month Z14 is punching through that fog. It's already luminous. It's already compact and organized enough to produce a clean spectrum. Something went wrong with the timeline. Maidu put it plainly. The early universe, he said, looks nothing like what we predicted. That assessment is both honest and striking. This isn't a minor calibration correction. This isn't the kind of slight revision that gets a footnote in a textbook. When the person who led the team that found the most distant confirmed galaxy in history says the universe looks nothing like the predictions, that's the field registering a genuine shock. The universe at 280 million years old was barely out of the cosmic dark ages. The dark ages began after the Big Bang's initial heat faded, when the universe cooled enough for neutral hydrogen to form. That hydrogen absorbed almost all the light in the cosmos, leaving the universe opaque and featureless for hundreds of millions of years. The first stars and galaxies began igniting somewhere in that darkness, their ultraviolet radiation slowly eating away at the hydrogen fog in a process astronomers call reionization. That process was supposed to be gradual, slow, driven by enormous numbers of small, faint objects collectively chipping away over hundreds of millions of years. Month-over-month Z14 isn't behaving like a minor participant in a long, slow process. It's sitting in the middle of what should still be fog, shining brightly, already showing the kind of luminosity that suggests something much further along in its development than the timeline allows. The record month-over-month Z14 holds right now will almost certainly be broken. Webb isn't finished. It's still accumulating observation time, still flagging candidates, still turning NIR spec toward the most extreme objects in its field of view. Before Webb launched, astronomers ran detailed forecasts of what the telescope would find. They predicted how many bright galaxies would exist at these extreme redshifts, based on the standard models of how galaxies form and grow. Those predictions already look embarrassingly conservative. Webb has found far more bright early galaxies than any of those models allowed for. It's not a small discrepancy. It's not a factor of 2. The numbers are off by orders of magnitude, and according to the astronomers running the survey, Webb is on pace to find 100 times more galaxies like it than anyone predicted before launch. The issue isn't just that these early galaxies exist, it's how much they weigh. When astronomers talk about a galaxy's mass, they're not talking about the mass of its gas or its dust or its central black hole. They're talking about stellar mass, the combined mass of every star inside it. And stellar mass doesn't just appear, it has to be built, one generation of stars at a time, through a process that takes an enormous amount of time. A cloud of gas collapses, a star ignites. That star burns through its fuel over millions or billions of years. It dies. The heavier elements it forged in its core get scattered back into space. A new generation of stars forms from that enriched material. Each step takes time. There's no shortcut. You can't rush stellar evolution any more than you can rush a tree growing from a seed. The universe has rules about this, and those rules set hard limits on how much stellar mass can accumulate within a given amount of time. Before Webb launched, cosmologists had run the numbers. They knew how old the universe was. They knew roughly when the first stars could have started forming. And from that, they could calculate an upper limit, the absolute maximum stellar mass a galaxy could have assembled by any given point in cosmic history, even under the most favorable conditions imaginable. These weren't rough guesses. They were careful mathematical limits derived from decades of observations and well-tested models of stellar physics. The models said that in the first few 100 million years after the Big Bang, only small, low-mass galaxies should exist. Faint, disorganized, primitive. The universe simply hadn't had enough time to produce anything larger. Webb found galaxies that blew past those limits, not slightly, not by a margin that might be explained away by measurement uncertainty or instrument calibration. Some of the galaxies Webb identified in the early universe carry stellar masses that the models said were flat out impossible at those epochs. Think about what that means. Not unlikely, not unexpected. Impossible, according to the best theoretical frameworks we had. It's like walking into a forest that you know for a fact was completely bare 50 years ago and finding a 500-year-old oak tree. The tree is undeniably there. You can measure it, you can count the rings, but the timeline doesn't work. There hasn't been enough time for it to grow, and yet there it stands. Our brains didn't evolve to feel the weight of that contradiction. But the astronomers staring at Webb's data felt it immediately. These weren't anomalies at the edge of the acceptable range. Some of the most extreme cases showed galaxies with stellar masses 10 to 100 times higher than the theoretical maximum for their age. You can't fix that with a small correction. That's not a rounding error. That's something being fundamentally wrong with the picture. Part of what makes this so troubling is the nature of stellar mass accumulation itself. Stars don't just form in isolation. The first generation of stars in the early universe was made almost entirely from hydrogen and helium, the only elements the Big Bang produced in significant quantities. Those first stars were likely enormous and short-lived, burning through their fuel in just a few million years before dying in catastrophic explosions. Those explosions seeded the surrounding gas with heavier elements, carbon, oxygen, iron. The next generation of stars formed from that enriched material, and they behaved differently. They were generally smaller, longer-lived, more like the stars we see today. Each generation builds on the last. It's a slow, layered process. For a galaxy to have accumulated a truly massive stellar population, it needs multiple generations of star formation, multiple cycles of birth, life, and death. That takes time, and the early universe simply didn't have it. Then Webb started finding the spiral galaxies. That's when things got even harder to explain. One of those galaxies is called Alaknanda. It was spotted just 1.5 billion years after the Big Bang, and it has spiral arms. Beautiful, organized, sweeping spiral arms, exactly like the ones you'd find in a mature, settled galaxy in the modern universe. The problem is that 1.5 billion years after the Big Bang, galaxies weren't supposed to look like that. At that epoch, the Standard Model predicted violent, chaotic conditions. Galaxies were colliding, merging, tearing apart and reforming. The early universe was a turbulent place, with galaxies crashing into each other constantly, their gravitational interactions shredding any delicate structure before it could stabilize. Spiral arms don't survive in that environment. They require time and relative calm to form. The galaxy's disk has to settle. The rotational dynamics have to stabilize. The gravitational forces have to organize themselves into those sweeping, curved patterns over hundreds of millions of years. It's not something that snaps into place overnight. And yet, there was Alexander, with its spiral arms intact, in an era when such a thing had no business existing. It wasn't alone. Webb has now identified more than 1,000 disk galaxies in the early universe, not just a handful. More than 1,000, that's 10 times more than the models predicted. 10 times. If the models had said something like 200, finding 1,000 would be surprising but perhaps explainable. You'd look for subtle adjustments, second-order effects that might account for the difference. But when you find 10 times more of something than you expected, you're not looking at a fine-tuning problem. You're looking at something genuinely missing from the picture. Spiral structure, ordered disks, gravitational stability, these are the hallmarks of mature galaxies. Finding them in abundance this early is like discovering that a city had already been fully built and populated decades before anyone laid the first brick. So what could explain it? Astronomers have explored several possibilities. Maybe star formation in the early universe was dramatically more efficient than it is today. In the modern universe, only a small fraction of available gas actually collapses into stars. Most of it gets blown away by radiation pressure, stellar winds, supernova shock waves. These feedback mechanisms act like a governor on the engine, slowing star formation down. But in the early universe, conditions were different. The gas was denser. The dark matter halos were more compact. Perhaps feedback was less effective, and star formation ran hotter and faster, converting gas into stars at a rate we simply don't see anywhere in the modern cosmos. That would explain the mass problem, at least partially. If early galaxies were turning gas into stars 10 or 20 times more efficiently than our models assume, the numbers start to look more manageable. But the spiral structure problem is harder to solve with efficiency alone. Efficiency explains mass. It doesn't explain order. It doesn't explain why galaxies that should have been chaotic and turbulent were already showing signs of gravitational calm. There's something else going on. And right now, no single modification to the Standard Model cleanly resolves both problems at once. The mass problem and the structure problem might be connected. They might not be. Astronomers are still working through the possibilities, running new simulations, looking for explanations that fit all the data simultaneously. What they haven't found yet is one that does. Either star formation in the early universe was operating at an efficiency that our current physics can't explain, or we're missing something deeper. Among everything Webb has found in the early universe, two categories of objects have proven the most difficult to explain. Not difficult in the sense that astronomers need a few more months to work out the details. Difficult in the sense that these objects shouldn't exist under any straightforward reading of current physics. They don't fit. They don't slot neatly into known categories and wait politely to be understood. They represent something genuinely new, and the scientific community is still working out what to do with them. The first category has a name that tells you something about the reaction astronomers had when they found them. Blue monsters. The name isn't informal slang. It reflects a real observational property. These objects appear blue in Webb's imaging, meaning they're emitting enormous amounts of light at shorter wavelengths. And they're compact. Extraordinarily compact. You're looking at sources that are physically small, far smaller than a typical galaxy, yet blazing with luminosity that rivals or exceeds galaxies many times their size. That combination is the problem. Brightness is not free. It has to come from somewhere, and the only known sources of that much light, packed into that smaller volume, are stars. A lot of stars. More stars than the available space can reasonably hold. Here's why that's a hard limit, and not just an inconvenience. When stars form, they don't form in silence. The process of nuclear fusion igniting inside a new star produces intense radiation that pushes outward against the surrounding gas. That radiation pressure is real and powerful. It works against gravity. If you try to pack too many forming stars into too small a region, the radiation from the first stars to ignite disrupts the gas that the next stars would need to form from. The process shuts itself down. It's not that astronomers are being conservative or cautious when they say there's a density limit on stellar populations. The physics of star formation imposes that limit directly. You cannot simply compress more and more stars into a smaller and smaller space. At some point, the whole process breaks down. Blue monsters appear to violate that limit. Their brightness, if it comes from stars, and that's the most obvious explanation, requires a concentration of stellar mass that shouldn't be achievable through any normal star formation process we understand. The stars would have to be packed so tightly that the radiation from the first generation would have destroyed the conditions needed to form the second generation before those stars ever got started. Think about what that means. These objects are either doing something our models of star formation don't account for, or they're not primarily powered by stars at all. Neither answer is comfortable. Some researchers have suggested that blue monsters might not be stellar populations in the conventional sense. There are theoretical objects called dark stars, hypothetical, never directly confirmed, that would be powered by a completely different mechanism. Those will come up later. For now, the point is that the simple explanation, that these are just very densely packed collections of ordinary stars, doesn't survive contact with the physics. The brightness requires a density. The density isn't achievable. That's the paradox, and it hasn't been resolved. The second category is stranger in a different way. Across Webb's deep field images, astronomers have catalogued large numbers of compact reddish sources that don't correspond cleanly to anything in the existing classification system. These are the little red dots. The name is again fairly literal. They appear as small, red objects in the infrared data, numerous enough that once astronomers started looking for them, they found them scattered throughout the observations in numbers nobody had anticipated. What are they? That question is genuinely open. The leading candidates break down into a few possibilities, and none of them are entirely satisfying. One possibility is that little red dots are extremely dense stellar populations, galaxies or proto-galactic cores where star formation is happening at such a furious rate. The resulting dust and gas are so thick that the light gets absorbed and re-emitted at longer, redder wavelengths. That would explain the red color. It would explain the compact appearance. The problem is the numbers. There are too many of them. The stellar masses implied by that explanation push back into the same territory as the size problem discussed in the previous section. Masses that are hard to explain given the age of the universe at these redshifts. The second possibility is that many little red dots are active galactic nuclei. At the center of most large galaxies, including our own Milky Way, sits a supermassive black hole. When material falls into one of these black holes, when it accretes, enormous amounts of energy are released. An actively accreting supermassive black hole can outshine the entire galaxy surrounding it. These objects are called quasars, or more generally, active galactic nuclei. They're compact by definition, because the energy is coming from a small central region, and the radiation from an accreting black hole can produce exactly the kind of red color Webb is detecting in these objects, if the light is filtered through surrounding dust. So the little red dots might be early supermassive black holes, already accreting material just a few 100 million years after the Big Bang. That explanation sounds tidy until you think about what it requires. Supermassive black holes don't appear from nothing. They have to grow. Growing a black hole massive enough to produce that much luminosity, in the available time, runs into the same basic problem as the massive galaxies. There simply hasn't been enough time for the standard growth mechanisms to produce what we're seeing. A black hole grows by consuming mass. That process has a speed limit, called the Eddington limit. That describes the maximum rate at which a black hole can accrete without the radiation it produces pushing the infalling material away. Growing a supermassive black hole from a stellar mass seed to something capable of powering a luminous quasar takes time. The universe at these early epochs may not have had that time, which leaves the third possibility, that many little red dots are some combination of both, dense stellar populations and active central black holes simultaneously, mixed together in a way that we haven't fully disentangled yet. That's not a resolution. That's an acknowledgement that the situation is complicated. Astronomers working with the data are frank about this. The spectroscopic signatures of some little red dots show features consistent with both hot young stars and accreting black holes. Separating those contributions cleanly is technically demanding work that is still ongoing. What makes all of this worse, or more interesting, depending on how you look at it, is the population statistics. Individually, you might accept that any one unusual object could be the result of rare circumstances, a peculiar alignment, an unusual chain of events that happen to produce something extreme. Science allows for outliers, but little red dots are not rare. They appear across Webb's observations in numbers that force the question into a different register. If these objects require unusual conditions to form, those conditions apparently weren't unusual at all in the early universe. They were common. Whatever physical process produces a little red dot was operating at scale, across enormous volumes of space during the first billion years of cosmic history. That's a category problem, not a detail problem. You don't fix a category problem by adjusting a parameter in an existing model. You fix it by reconsidering the model itself, by asking whether the assumptions baked into our understanding of early black hole growth, early star formation, early galactic structure are actually correct. The blue monsters suggest that stellar density limits may have been operating differently than expected, or that something other than stars is responsible for extreme early luminosity. The little red dots suggest that either supermassive black holes were forming and growing at rates the standard picture doesn't allow, or that star formation in the early universe was operating in a regime we haven't properly characterized. Both categories were essentially unknown before Webb. Neither one has a clean explanation. The problem isn't that one or two of these objects exist, it's that there are thousands of them. Before the first stars ignited, the universe was dark. Not dark the way a room gets dark when you turn off the lights. Not dark the way the night sky looks between the stars. A different kind of dark entirely. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma, a soup of charged particles so energetic that light couldn't travel through it at all. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly light could move freely. That moment is called recombination. The light released then is still detectable today as the cosmic microwave background. But what came after recombination wasn't brightness. It was a void. The universe had no stars yet, no galaxies, no sources of light anywhere, just an expanding fog of neutral hydrogen gas, cold and dark and featureless, stretching in every direction. Astronomers call this period the Cosmic Dark Ages. It lasted hundreds of millions of years. Then something changed. The first stars ignited. The first galaxies began to form, and the ultraviolet radiation they pumped into the surrounding gas started stripping electrons away from hydrogen atoms, converting neutral hydrogen back into ionized plasma. This process is called reionization. It's one of the most important transitions in the entire history of the universe. It's the moment the cosmos switched on. The fog lifted. The universe became transparent to ultraviolet light in a way it hadn't been since those very first moments after the Big Bang. And after that, the universe started looking like the universe we know, filled with stars, galaxies, and light. The Standard Model had a very specific story about how this happened. Reionization, according to that story, was a slow and democratic process. It was driven primarily by enormous numbers of small, faint galaxies, each one contributing a modest trickle of ionizing ultraviolet radiation. No single galaxy was powerful enough to make much difference on its own, but there were millions of them, spread across the young universe. Collectively, their combined output was enough to chip away at the neutral hydrogen fog over hundreds of millions of years. Think of it like rainfall filling a reservoir. No single raindrop makes a visible difference, but enough of them, falling steadily over a long enough time, eventually do the job. That was the prediction. Slow, distributed, driven by the faint majority. Webb is finding something different. What the telescope keeps seeing is bright, massive galaxies playing a far larger role in reionization than anyone anticipated. Not just contributing a modest share of the ionizing photons, actually dominating in certain regions, punching through the neutral hydrogen fog with enough force to carve out large bubbles of ionized space around themselves. The clearest example of this is month-over-month Z14, the most distant galaxy ever confirmed, existing just 280 million years after the Big Bang. When astronomers analyzed the data, they found evidence that month-over-month Z14 was already clearing the fog in its local environment. It wasn't waiting for a slow accumulation of radiation from countless faint neighbors. It was doing it on its own. One galaxy, 280 million years into the history of the universe, already powerful enough to ionize its surroundings. That's not what the models predicted, not even close. Think about what that means for the timeline. If the small, faint galaxies were supposed to be the primary drivers of reionization, if reionization was supposed to be a gradual process spread over several 100 million years, then the discovery of bright, massive galaxies dominating local reionization changes the entire picture. Reionization might have started earlier than expected. It might have progressed faster in certain regions than the models allowed. It might have been deeply uneven, not a uniform lifting of the fog across the whole universe, but a patchy process where some regions cleared out quickly around massive bright galaxies, while other regions stayed neutral much longer. The fog didn't lift uniformly like a sunrise. It might have cleared in holes and pockets, driven by the brightest, most powerful sources, spreading unevenly across hundreds of millions of light years. That patchiness matters. The standard picture had reionization finishing around 1 billion years after the Big Bang, wrapping up cleanly as the accumulated radiation from countless faint galaxies finally pushed the remaining neutral hydrogen below a critical threshold. But if the bright galaxies were doing more of the work, the timeline and the geometry of the whole process shifts. Some regions might have been ionized and transparent much earlier. Others might have stayed foggy much longer. The sequence of events in the universe's first billion years looks different, and the first billion years of cosmic history aren't a footnote, they're the foundation. That's when the first stars formed, when the first heavy elements were created, when the cosmic web of dark matter began organizing matter into the structures that would eventually become everything we see today. The awkward truth is that before Webb, astronomers were largely guessing about the details of reionization. Not guessing wildly, the predictions were built on solid physics and decades of theoretical work, but the actual direct evidence was thin. Detecting the spectroscopic signatures of neutral hydrogen fog at extreme redshifts, mapping which galaxies were ionizing which regions and when, watching the fog clear in real time across different cosmic locations that required an instrument sensitive enough to take spectra of galaxies existing 13 billion years ago. No telescope before Webb could do that. So the models were built on indirect evidence, on extrapolations, on assumptions about how many faint galaxies existed and how much ionizing radiation they produced. Those assumptions seemed reasonable. They aren't holding up. Webb's NISPEC instrument is now taking the first real spectroscopic census of galaxies at these extreme redshifts. hundreds of spectra, mapped across different cosmic epochs, showing how the neutral hydrogen content of the universe changed over time and which galaxies were driving that change. The results keep coming back wrong relative to the predictions. Bright galaxies are more common than expected. Their individual contributions to ionization are larger than expected. The faint majority that was supposed to carry most of the load is still there, still contributing, but it's no longer the whole story. The dominant narrative of reionization is being revised line by line as the data comes in. And this isn't a minor adjustment to a footnote in cosmological history. Reionization is the pivot point between the dark ages and the luminous universe. Getting it right means getting the sequence of early cosmic events right. It means understanding when the first stars could form, how the first galaxies grew, how the heavy elements created in those first stellar generations got distributed through the universe. Every stage of that story connects to the next. If the opening chapter is different than we thought, the pages that follow are different too. The astronomers doing this work are careful about their language. They're not declaring the models broken, but they're also not pretending the data fits. Every new spectrum Webb takes of these early galaxies is rewriting the timeline of how the universe first turned on the lights. Not every mystery Webb uncovered in the early universe is about things being bigger or brighter than expected. Some of what the telescope found points in the opposite direction. Galaxies that had stopped, systems that had gone dark, massive structures in the early universe that had somehow run out of fuel and died, long before any model said they should have. This is a different kind of problem, and in some ways it's just as troubling as the size problem. In the modern universe, dead galaxies are common. You find them throughout the local cosmic neighborhood. Enormous elliptical galaxies, red and fading, no longer producing new stars coasting on the light of whatever stellar population formed billions of years ago. Astronomers call them quiescent galaxies. They're expected. They make sense. Stars consume the available gas. Feedback from supernovae and black holes heats what remains. And eventually the raw material for new star formation just runs out. That process takes time, a lot of it, which is why it was so strange when Webb started finding dead galaxies in the early universe. Massive systems, billions of solar masses worth of stars, that had already stopped forming stars when the universe was only a fraction of its current age. The universe hadn't had time to slowly wind these galaxies down. Something had switched them off. This was not a new puzzle when Webb launched. Astronomers had seen hints of early quiescent galaxies before, through Hubble and ground-based observatories. But the sample was small and the measurements were uncertain. Webb changed that. Its infrared sensitivity and spectroscopic precision allowed astronomers to study these objects in real detail, to measure their stellar populations, their gas content, their internal dynamics. And what came back was clear. These galaxies were genuinely dead, not fading, not slowing down, dead. The question was what killed them. The leading answer involves gas. Specifically, the violent removal of it. When galaxies grow large enough, the supermassive black holes at their centers begin to matter. As material falls toward one of these black holes, it doesn't simply vanish. It forms an accretion disk, heating up to extraordinary temperatures, releasing enormous amounts of energy as radiation and as fast-moving jets of particles. That energy has to go somewhere. It plows into the surrounding gas. It heats it. It accelerates it. In some cases, it launches it out of the galaxy entirely. This process is called AGN feedback, where AGN stands for active galactic nucleus, and it's been part of galaxy formation models for years. The idea that black holes regulate their own host galaxies by heating or expelling gas is not new, but what Webb is showing is that this process was operating far more aggressively and far earlier than models predicted. Galactic mergers accelerate things further. When two massive galaxies collide, the gravitational chaos compresses gas, triggers enormous bursts of star formation, and drives more material toward the central black holes of both systems. The black holes can grow rapidly. The feedback intensifies. Gas that might have been quietly forming stars for billions of years gets swept up and flung outward at tremendous speed. The result is a galaxy that builds up enormous stellar mass very quickly, then has the gas that could have built even more mass violently expelled. Using Webb alongside the Atacama Large Millimeter Array, astronomers detected one of these winds directly. ALMA observes at radio and millimeter wavelengths, which makes it sensitive to cold gas, the raw material for star formation. Webb observed the stellar populations and the ionized gas. Together, the two telescopes gave astronomers a complete picture of what was happening inside a distant early galaxy undergoing this process. What they found was a wind, an outflow of gas moving at thousands of kilometers per second. Not a gentle dispersal, not a slow leak, a blast. Gas being ejected from the galaxy at a rate and velocity sufficient to strip the system of its star-forming fuel entirely. Think about what that means in terms of scale. A galaxy might contain billions of solar masses worth of gas. That gas represents the raw material for potentially billions of future stars, billions of years of continued star formation. A wind powerful enough to eject it is not a minor event. It is the end of the galaxy's productive life. Once that gas is gone, pushed out into the intergalactic medium, there is nothing left to make new stars from. The existing stellar population continues to age, to cool, to fade. No new light replaces it. The galaxy goes quiet. And this appears to have been happening routinely in the early universe, not occasionally, not in extreme rare cases, routinely. Webb found large numbers of massive quiescent galaxies at high redshifts, more than models had predicted, which means this killing mechanism was operating across a significant fraction of the early galaxy population. The cycle was fast and brutal. Gas collapses, a galaxy forms, stars ignite, a black hole grows. Mergers accelerate everything. The wind fires, the gas is gone, the galaxy dies. All of this, in some cases, within 1 billion years or less. That timeline is what makes this finding so difficult to absorb. 1 billion years sounds like a long time. By human standards, it is incomprehensible. But in cosmic terms, a galaxy that forms and dies within 1 billion years is essentially a mayfly. The standard model had predicted a much more gradual process. Slow build-up, slow quenching, galaxies spending billions of years in transition states before going fully dark. Webb is showing a universe that moves faster than that. A universe where the mechanisms of creation and destruction were both operating at elevated intensity on compressed timescales in ways the models simply didn't have room for. And this creates one more layer of the problem that astronomers haven't resolved. If these galaxy-killing winds were so efficient, if they could strip a massive galaxy of its gas in a cosmically short period of time, then how did some of those galaxies manage to grow so enormously large before they were killed? The same mechanism that terminates star formation should have been interfering with the growth process all along. Something was allowing rapid assembly despite the feedback. Something was letting these galaxies accumulate mass faster than the winds could remove it, at least temporarily. What that something is remains an open question. The same telescope that found galaxies too massive to exist also found them dying too fast to explain. While astronomers were grappling with the mass problem, Webb turned up something else. The early universe was already in chaos. The assumption had always been that the early universe needed time to organize itself. Matter had to clump together slowly under gravity. Small structures had to form first. Then those small structures would gradually merge into larger ones over billions of years. The cosmic web, the vast scaffolding of dark matter filaments that threads through the universe, was supposed to build up gradually, pulling galaxies together along its strands over enormous stretches of time. That was the model. That was what the simulations predicted. And then Webb started showing astronomers what was actually out there at 800 million years after the Big Bang, and the timeline collapsed. Researchers at Texas A&M University identified something extraordinary in Webb's data. At least 5 galaxies, already fully formed, already in a tight cluster, already crashing into each other, not drifting close together, not beginning to interact at the edges, actively colliding 800 million years after the Big Bang. And the collision wasn't just a gravitational brush. There was evidence that heavy elements, carbon, oxygen, the kind of material that only gets forged inside stars, were already being redistributed by the merger, scattered outward, mixed through the surrounding gas. Think about what that requires. For 5 galaxies to be colliding at 800 million years, those galaxies had to already exist. They had to have formed, grown massive enough to matter gravitationally, and then been drawn together along filaments of dark matter into collision courses. All of that had to happen in less than 800 million years. The dark matter web had to be structurally complete enough to funnel those galaxies toward each other. The galaxies had to have generated enough heavy elements for those elements to show up in the wreckage of the merger. Every single step in that chain had to happen faster than the models allowed. Our brains didn't evolve to feel the weight of that timeline, but 800 million years sounds like a long time until you realize the universe is 13.8 billion years old. That merger was happening when the universe was barely 6% of its current age. In human terms, it would be like finding a major city already burning down before the civilization that built it was supposed to have even invented agriculture. The cosmic web itself is the key issue here. It's not something you can see directly. Dark matter doesn't emit light. You infer the web's existence from the way galaxies cluster together, strung out in filaments, concentrated at nodes with vast empty voids in between. The standard model predicted this structure would take considerable time to develop. The filaments had to thicken. Galaxies had to accumulate at the intersections. Only then would mergers of significant scale become possible. What Webb found suggests the web was doing its job far earlier and far more completely than anyone expected. The infrastructure was already in place. The highways were already built. The traffic was already moving. Webb's NIRCam, its near-infrared camera, gave astronomers a way to study not just where early galaxies were, but what was happening inside them. And what it found was turbulence. Gas moving rapidly in multiple directions. Chaotic flows with no settled structure. When researchers tracked the gas dynamics in over 250 early galaxies, they weren't seeing the orderly rotating disks that characterize galaxies like the Milky Way. They were seeing something messy, something unsettled, something that looked less like a galaxy and more like a violent, ongoing event. The analogy that keeps coming up is a simple one. Early galaxies were like toddlers, loud, chaotic, constantly colliding with things, throwing material in every direction, incapable of settling into a stable pattern for more than a moment. Modern galaxies, mature spirals with well-defined arms, orderly stellar populations, quiet central bulges, are the settled adults. They got that way because the available gas was consumed by successive generations of stars, because the violent interactions of youth gradually gave way to something more stable, because billions of years smoothed out the disorder. Early galaxies hadn't had that time. They were still in the middle of becoming whatever they were going to be. But here is where it gets genuinely strange, because running alongside that picture of chaotic, turbulent early galaxies is a completely different set of observations. Webb found Alaknanda, a mature spiral galaxy with well-defined structure, just 1.5 billion years after the Big Bang. It found more than 1,000 disk galaxies in the early universe, 10 times more common than expected, in an era when violent mergers were supposed to make such delicate structures impossible. Disk galaxies require time and relative calm to maintain their form. The gravitational forces during an active merger should tear spiral structure apart, and yet there they are. So the early universe was simultaneously producing galaxies with fragile, structured forms and hosting wildly chaotic merger events. Both things were true at the same time. That's not a slight tension in the data. That's a genuine contradiction, and it doesn't resolve neatly with small adjustments to the existing models. Something about how rapidly galaxies formed, how efficiently dark matter organized itself, how quickly the cosmic web assembled its structure, something is fundamentally different from what we assumed. The implications ripple across multiple scientific disciplines. Astrophysicists studying star formation had to reconsider their models for stellar population assembly. Cosmologists examining the distribution of dark matter found their simulations produced galaxies far too slowly. Computer scientists working on numerical simulations discovered that simply increasing processing power wasn't enough. The underlying physics assumptions needed fundamental revision. The data forced a complete reckoning. Every subdiscipline that touched the question of early galaxy formation found itself forced to explain why their models had systematically underestimated how rapidly the universe could organize itself. What the complete picture describes is an early universe that wasn't gently warming up, wasn't slowly building from simple to complex, wasn't giving structure all the time it needed to develop on a careful schedule. It was running multiple processes simultaneously at speeds the models had no room for. Mergers at 800 million years, spiral structure at 1.5 billion years, bright massive galaxies at 280 million years, turbulent chaotic gas coexisting with delicate organized forms. The whole thing was already in motion, already complex, already violent, already structured in ways that required far less time than anyone predicted. The early universe wasn't slowly waking up, it was already running. When normal explanations stop working, physicists start reaching for stranger ones. Everything Webb has found in the early universe, the impossible masses, the blue monsters, the little red dots, has pushed theorists to the edge of what standard physics can accommodate. Most of the proposed solutions involve tweaking the existing model. Maybe star formation was more efficient. Maybe feedback mechanisms worked differently. Maybe our mass estimates are slightly off. These are reasonable adjustments. Scientists make them all the time. But there is one proposed explanation that doesn't tweak anything. It throws out a fundamental assumption entirely. It suggests that some of the objects Webb is seeing aren't made of stars at all. Not in the normal sense. They're powered by something else completely. Something that has never been directly observed. Something that until recently most astronomers would have hesitated to mention in a serious paper. They're called dark stars. The theory isn't new. It predates the James Webb Space Telescope by more than a decade. Physicists first proposed the concept around 2007, working through the theoretical conditions of the very early universe. Their reasoning started with dark matter. We know dark matter exists. We can measure its gravitational effects. It holds galaxies together. It shapes the large-scale structure of the cosmos. What we don't know is what dark matter actually is. One leading candidate is a class of particles called WIMPs, weakly interacting massive particles. And here's the critical detail. Under certain conditions, when two WIMP particles collide, they annihilate each other. They convert their mass directly into energy. In the modern universe, dark matter is spread thin enough that these annihilation events are rare. But in the very early universe, dark matter was far more densely packed. The first stars were forming inside dense dark matter halos, and inside those halos, the concentration of dark matter was high enough that annihilation events could have been happening constantly, releasing enormous amounts of energy directly into the cores of forming stars. Think about what that means. A normal star is powered by nuclear fusion. Hydrogen atoms fuse into helium. The energy released creates outward pressure that holds the star up against its own gravity. That's how every star we've ever seen works. But a dark star would have a completely different energy source. The annihilating dark matter particles in its core would generate heat before fusion ever ignited. The star would be supported by that heat. It would never need to fuse hydrogen at all, at least not initially. And because the energy source is different, everything about the star would be different too. Dark stars, if they existed, would have been enormous. We're talking about objects potentially millions of times more massive than the Sun. Not thousands, millions. They would have been cool at the surface, much cooler than normal massive stars, because their energy output, while substantial, was spread across an enormous volume. That cooler surface temperature would give them a reddish appearance, and they would have been luminous, not as intensely bright per unit area as a hot blue star, but enormous enough in size that their total light output could have been staggering. Here's where the Webb observations become relevant. The blue monsters are extraordinarily luminous, compact, bright beyond what normal stellar populations can explain. Standard models look at the brightness of a blue monster and say, to produce that much light, you would need to pack an impossible number of stars into that volume. The density required exceeds what stellar physics allows. Stars can't form arbitrarily close together. Radiation pressure, gravitational dynamics, these impose hard limits. You simply cannot cram enough stars into that space to generate that much light through normal fusion. The physics doesn't permit it. But what if it isn't a dense cluster of stars at all? What if it's one object? A single dark star, massive enough to produce the observed luminosity all by itself, would eliminate the density paradox entirely. You don't need to pack in a billion stars. You need one enormous object powered by a completely different mechanism. The size and luminosity suddenly become explainable. Not easily, and not without other complications, but explainable in a way that no amount of tweaking star formation efficiency can achieve. Think of it like a murder mystery. You have a crime scene that doesn't make sense. The most obvious suspect has an airtight alibi. Standard star formation cannot do this. So you start looking at less obvious suspects. You start asking whether something else entirely was present that night. Dark stars are the exotic suspect, the one you'd normally dismiss. But when the obvious answer keeps failing, you at least have to look at the strange one. Astronomers are appropriately cautious. Dark stars have never been observed. No confirmed detection, no direct evidence. The theory rests on assumptions about dark matter particle properties that haven't been experimentally verified. We don't even know for certain that WIMPs are the right dark matter candidate. If they're not, the entire energy mechanism falls apart. And even if WIMPs exist, the conditions required for dark stars to form may never have actually occurred in the early universe, despite the theoretical possibility. So how do you test this? What would confirm or rule out dark stars? Part of the answer is spectroscopy. A dark star would have a distinct spectral signature. Its light would carry chemical fingerprints different from a galaxy packed with millions of ordinary stars. The spectrum of a massive, cool, diffuse object looks different from the spectrum of a compact stellar cluster. Webb's NIR spec instrument is precisely the tool that could, in principle, detect that difference. If astronomers identify a candidate object and its spectrum matches what dark star models predict, that would be significant. Not conclusive, but significant. Ruling them out is harder. The absence of a detection only tells you so much about an object billions of light years away. What's remarkable isn't that dark stars have been proven. They haven't been. What's remarkable is the conversation happening right now in astrophysics journals. Serious researchers at serious institutions are running the numbers on dark matter annihilation rates in early universe halos. They're publishing papers. They're modeling what dark stars would look like to Webb. This is not fringe science. It's a genuine theoretical response to genuine observational anomalies. The fact that it involves hypothetical objects powered by dark matter annihilation tells you something important. It tells you that the gap between what Webb is seeing and what the standard model predicts is wide enough that exotic physics is now on the table. Whether or not dark stars are real, the fact that they're being taken seriously tells you everything about how far the standard model is being stretched. Taken individually, any one of Webb's surprising discoveries could be explained away. A single unexpectedly massive galaxy could be a measurement error. One unusually bright early object could be a fluke. A handful of mature spirals showing up ahead of schedule could reflect natural variation in a model that already allows for some scatter. Scientists deal with outliers all the time. Outliers don't overturn theories. But Webb isn't showing us outliers. It's showing us a pattern, and the pattern runs in the same direction every single time. Every time the telescope looks deeper, the early universe looks more developed than it should. That's not noise. That's a signal. To understand why that signal matters so much, you have to understand what the Lambda-CDM model actually is. Lambda-CDM is the standard model of cosmology. It's the framework that nearly every working astronomer uses to describe how the universe formed and how it evolved. The name breaks down simply enough. Lambda refers to dark energy, the mysterious force accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible substance that makes up roughly 27% of the universe's total energy content. Together, those two components dominate the universe. Ordinary matter, everything you can touch, everything made of atoms, accounts for only about 5% of what exists. The model rests on a few core pillars: the Big Bang, the gradual expansion and cooling of the universe, the slow hierarchical assembly of structure, where small clumps of dark matter merge into larger ones over billions of years, dragging gas along with them and seeding the formation of stars and galaxies. The word hierarchical is important here. The model specifically predicts that small structures come first, large structures come later. You build galaxies from smaller pieces. You build galaxy clusters from galaxies. The process is slow and cumulative, and for decades Lambda-CDM was extraordinary. That's not an exaggeration. The model predicted the temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky, with remarkable precision. It predicted the large-scale distribution of galaxies across the observable universe, the vast web of filaments and voids we see when we map cosmic structure. It predicted the relative abundance of hydrogen, helium, and lithium forged in the first few minutes after the Big Bang. Every one of those predictions matched observations. The model wasn't just good, it was genuinely impressive. So when it starts struggling at the edges, that means something. Here's the honest situation astronomers are in right now. There are two broad possibilities, and they don't yet know which one is correct. The first is that Lambda-CDM is basically right. The framework is sound, but the early universe had conditions we didn't fully account for, conditions that allowed structure to assemble faster than the standard version of the model predicts. Star formation efficiency, for instance. In modern galaxies, star formation is surprisingly inefficient. Most of the gas available in a galaxy at any given time doesn't actually collapse into stars. Feedback processes, radiation pressure from young stars, supernova explosions, jets from black holes, all of these disrupt the gas and slow star formation down. If those feedback mechanisms were weaker in the early universe, or if they operated differently, star formation could have been dramatically more efficient. More stars forming faster means more stellar mass accumulating earlier. That could help explain what Webb is seeing without requiring any changes to the fundamental physics. The second possibility is more uncomfortable. The model itself has a deeper problem. Something about how dark matter behaves in the early universe, or something about the initial conditions set by inflation, the rapid expansion of the universe in its first fraction of a second, may be genuinely different from what the standard model assumes. If that's true, then the early universe physics isn't just harder to model, it's operating under different rules. Astronomers are actively exploring both directions. Some researchers are running simulations with much higher early star formation efficiencies, asking whether you can reproduce Webb's observations just by turning that dial up. Others are looking at modifications to dark matter behavior. Standard cold dark matter moves slowly, and clumps on all scales. Some alternative models propose dark matter that behaves differently on small scales, either clumping more efficiently in the early universe or interacting in ways the standard model doesn't allow. There are also proposals involving modifications to the inflationary period itself. The pattern of fluctuations left by inflation seeded everything that came after. If those initial fluctuations were slightly different from what the standard model assumes, the downstream effects billions of years later could be exactly what Webb is now detecting. None of these proposals are wild speculation. They're serious work being done by serious researchers, but none of them have been confirmed either. And here's the problem that runs through all of them. We don't yet have enough spectroscopically confirmed galaxies at extreme redshifts to do proper statistics. Think about what statistics requires. You need a large enough sample that you can separate real trends from random fluctuations. Right now, the number of galaxies with confirmed spectroscopic redshifts above 10, meaning galaxies we can say with real confidence existed when the universe was less than 500 million years old, is still measured in dozens. That's not enough to make definitive claims about how common these objects are, what their true mass distribution looks like, or how badly they conflict with model predictions at the population level. The observations are striking. The pattern is consistent, but the sample is small. What makes this genuinely hard is that the measurements themselves carry uncertainty. Stellar mass estimates for distant galaxies depend on modeling assumptions. You observe the galaxy's light, you model what stellar population would produce that light, and you infer the total stellar mass. That chain of inference has error bars. When a galaxy appears to be impossibly massive, part of the question is always whether the mass estimate is accurate, or whether something about the modeling, dust properties, the age distribution of the stellar population, the contribution from an active galactic nucleus is throwing the numbers off. Astronomers are working hard to nail down those systematics, but it takes time. Most cosmologists working today are cautious. They're not declaring the standard model broken. That would be premature, and scientists don't overturn frameworks on the basis of a few dozen anomalous data points, even striking ones. What they are doing is paying close attention, running new models, questioning assumptions they previously took for granted, asking whether the feedback mechanisms built into their simulations are correctly calibrated, asking whether the initial power spectrum of density fluctuations is exactly what they assumed. These are the right questions. This is how science is supposed to work. But there's a tension in that caution, because the surprises keep arriving. Each new observing cycle produces more galaxies that push the limits. The trend hasn't reversed. Webb hasn't started finding exactly what the models predicted once astronomers looked more carefully. If anything, the confirmed sample keeps expanding in ways that apply more pressure, not less. The standard model has survived every challenge thrown at it for decades, but it has never had to face so many surprises arriving so quickly from so far away. To understand what Webb is actually doing when it finds these galaxies, it helps to understand what makes this telescope different from anything that came before it. The most important thing about Webb isn't its size, although size matters. It isn't its orbit, although that matters too. The most important thing is what kind of light it sees. Webb was built to detect infrared light, not visible light, not ultraviolet, infrared. And that distinction is everything when you're trying to look at the earliest galaxies in the universe. Here's why. The universe is expanding. It has been expanding since the Big Bang, and as it expands, the light traveling through it gets stretched. A photon that started out as ultraviolet light when it left a galaxy 13 billion years ago doesn't arrive here as ultraviolet. The expansion of space stretches its wavelength during the journey, shifting it toward the red end of the spectrum, and then past it, out into the infrared. By the time the light from a galaxy like month-over-month C14 reaches us, it's been traveling for 13.5 billion years through an expanding universe. It arrives not as visible light, but as infrared radiation. If your telescope can't see infrared, you can't see that galaxy. You can't see most of the early universe at all. Hubble couldn't. That's not a flaw in Hubble's design. It simply wasn't built for this. Webb was. Hubble has a primary mirror 2.4 meters across. That's the diameter of a large dining table. Webb's primary mirror is 6.5 meters across. That's roughly the height of a two-story building. The mirror isn't a single piece of glass. It couldn't be because no rocket fairing is wide enough to carry a 6.5 meter mirror in one piece. Webb's mirror is made of 18 hexagonal gold-coated beryllium segments that folded up for launch and then unfolded in space. Gold was chosen as the coating because it reflects infrared light with exceptional efficiency. Each segment had to be aligned to within a fraction of the wavelength of light. The precision involved is almost impossible to overstate. What does a bigger mirror actually give you? Two things: more light gathering power and sharper resolution. A mirror 6.5 meters wide collects about 7 times more light than Hubble's 2.4 meter mirror. That matters when you're looking at objects so distant and so faint that they'd be invisible to anything less capable. These early galaxies aren't bright. Some of them are among the faintest objects ever detected by any instrument ever built. Webb can find them because it can collect enough of their light to actually measure. Now, there's a problem with building an infrared telescope. Everything warm glows in infrared. Your body glows in infrared. A telescope sitting in sunlight glows in infrared. If Webb were operating anywhere near room temperature, its own thermal emission would completely overwhelm the faint infrared signals coming from 13-billion-year-old galaxies. The telescope would, in effect, be blinded by its own glow. To prevent that, Webb has to be extraordinarily cold. It operates at around 40 Kelvin. That's roughly minus 233 degrees Celsius. Colder than Pluto's surface, almost at absolute zero. To stay that cold, Webb needs to be kept out of sunlight permanently. That's a large part of why its location was chosen so carefully. Webb sits at a gravitational point in space called the second Lagrange point, or L2, about 1.5 million kilometers from Earth in the direction directly away from the Sun. At L2, the gravitational forces of Earth and the Sun combine in a way that allows an object to orbit the Sun at the same rate Earth does, staying in a fixed position relative to both. Webb's enormous sun shield, roughly the size of a tennis court, keeps the Sun, Earth and Moon all on one side, permanently shading the telescope. The cold side of Webb stays cold. The instruments stay sensitive. The faint signals from ancient galaxies have a chance of being detected. Getting Webb to L2 was itself an extraordinary engineering challenge. The telescope launched on Christmas Day 2021 on an Ariane 5 rocket from French Guiana. The trajectory had to be precise enough to deliver Webb to its target without wasting fuel. Fuel matters because Webb has no way to be refueled. Once it's spent, the telescope's operational life ends. The Ariane 5's trajectory was so accurate that Webb arrived at L2 having used far less propellant than the conservative mission planning had budgeted for. The original baseline mission was 10 years. Because of the fuel saved during launch, current estimates suggest Webb could operate for 20 years or more. Discoveries that weren't supposed to happen until the 2030s might happen in the late 2020s instead. When Webb finds a candidate galaxy, a bright object at extreme distance, imaging alone isn't enough to confirm what it is. That's where the NIR SPEC instrument comes in. NIR SPEC stands for Near Infrared Spectrograph. Instead of capturing an image, a spectrograph splits the incoming light into its component wavelengths, the way a prism splits white light into a rainbow. That spread of wavelengths is called a spectrum, and it carries an enormous amount of information. Different chemical elements absorb and emit light at specific wavelengths, leaving distinctive fingerprints. By reading those fingerprints in a galaxy's spectrum, astronomers can determine its chemical composition, its temperature, how fast it's moving, and critically, its redshift. A galaxy's redshift tells you directly how much its light has been stretched by cosmic expansion, which tells you exactly how far away it is and how old the light is. This is how month-over-month Z14 was confirmed at a redshift of 14.44. Photometric imaging flagged it as a candidate. NI-SPEC confirmed it. That distinction matters. Photometric estimates can be wrong. Spectroscopic measurements don't leave the same room for error. Think about what this all adds up to. A mirror large enough to collect light from objects that are effectively invisible to any earlier instrument. A sensitivity to infrared that captures light stretched by 13.5 billion years of cosmic expansion. A temperature cold enough to prevent the telescope from drowning out its own targets. A location stable enough to maintain that temperature indefinitely. A spectrograph precise enough to read chemical fingerprints from across the observable universe. None of the galaxies Webb is finding are new. They've been out there the entire time, radiating, drifting, evolving, waiting. The light from these ancient galaxies has been traveling toward us for over 13 billion years. We just finally built something sensitive enough to receive it. The individual galaxy discoveries are remarkable on their own, but what Webb is really building is a map. Not a map of continents or ocean floors, a map of the entire observable universe, stretching back billions of years to the very first structures that ever formed. And to understand why that map matters, you first have to understand what it's being drawn on top of. The universe is not a uniform soup of galaxies distributed evenly through space. It has structure, enormous structure. Matter in the cosmos is organized into a vast network of filaments and voids, a web of dark matter and gas that spans everything we can observe. Galaxies don't float randomly through this web. They cluster at the intersections of the filaments, at the nodes where strands of the web cross each other. Think of dew collecting on a spider's web at the joints where threads meet. That's roughly how it works. The filaments themselves are mostly dark matter, invisible, detectable only through the gravitational influence they exert on everything around them. The gas and the galaxies trace those filaments. They follow the architecture that dark matter laid down. This entire structure is called the cosmic web, and it spans hundreds of millions of light years in every direction. The reason it looks the way it does goes back to the very beginning. In the first fraction of a second after the Big Bang, tiny quantum fluctuations, random variations in density, impossibly small, were stretched across the entire universe as space itself expanded. Those fluctuations left some regions of the early universe slightly denser than others, just slightly. We're talking about variations of roughly 1 part in 100,000. But gravity is patient. Over hundreds of millions of years, those denser regions pulled in more matter. The matter accumulated. The densest clumps became the first galaxies. The surrounding regions were drained. Over billions of years, the small fluctuations grew into the enormous filaments and voids we see today. Everything that exists, every galaxy, every star, every planet, traces its origin back to those tiny density variations in the first moments of the universe. The cosmic web is the grown-up version of the earliest structure in existence. That's why mapping the early universe matters so much. When Webb observes galaxies at redshifts above 10, it's looking at structures that formed in the first few 100 million years of cosmic history. That's less than 3% of the universe's current age. At those epochs, the cosmic web was still in its infancy. The filaments were thinner, the nodes were smaller. The galaxies clustered at those intersections were younger, less massive, and in theory less evolved. By charting where those early galaxies sit, how they cluster, how they're distributed through space, astronomers are mapping the scaffolding of the universe at the earliest moment we can observe it. They're tracing the skeleton of the cosmic web when it had barely begun to form. A complete census of early galaxies would answer questions we currently can't get close to answering. The rate of star formation over time is one of them. How quickly were early galaxies converting gas into stars? Was there a peak era of star formation? And if so, when? The distribution of dark matter in the early universe is another. We can't see dark matter directly, but we can infer its distribution from where the galaxies cluster. If the galaxies are concentrated along filaments in the early universe, those filaments tell you where the dark matter was. The timeline of reionization is another open question. When exactly did the neutral hydrogen fog clear, and how quickly did it happen in different regions? And then there's the growth of supermassive black holes. Every large galaxy today hosts a supermassive black hole at its center. How those black holes got so massive so quickly is one of the deepest unsolved problems in astrophysics. Webb is already detecting some of them feeding aggressively in the early universe. A full population census would tell you when and how they grew. Here's the thing about population statistics that's easy to miss. Any single galaxy, no matter how extreme, can in principle be explained away. An outlier is always possible. Maybe the conditions were unusual. Maybe there's a measurement error. Maybe it's a fluke. But when you find dozens of galaxies that all break the model in the same direction, all too bright, all too massive, all too structured, the fluke explanation collapses. Statistics are unforgiving that way. The more objects you have, the harder it becomes to dismiss the pattern. Webb is finding these massive early galaxies not one at a time, but in populations. Hundreds of candidates, dozens confirmed, and the confirmation rate keeps climbing as observation time accumulates. That's not a measurement error, that's a signal. At redshift 14, you're looking back 13.5 billion years. The light reaching Webb from those distances left its source when the universe was roughly 300 million years old. At redshift 10, it's still over 13 billion years ago. The universe was under 500 million years old. Webb is operating across this entire range, collecting light from galaxies at redshift 5, 8, 10, 12, 14 and beyond. Each redshift slice is a different moment in cosmic history. Each one adds another data point to the timeline. Enough data points and you can start reconstructing the full arc. How galaxy formation ramped up, how the cosmic web assembled, how the early universe transitioned from dark and neutral to bright and ionized. That timeline is what astronomers are piecing together right now, and it keeps coming out different from what the models predicted. What Webb is doing in practice is something like sifting through soil at an excavation site. Most of what it finds is expected. Background galaxies, foreground objects, familiar structures. But scattered through the data are objects that don't fit the expected picture. Galaxies that are too bright for their redshift, structures too organized for their age, populations too numerous for the models to account for. Each one is an artifact that forces a reassessment. Each one adds to a growing body of evidence that the early universe was doing something the standard picture didn't anticipate. The individual objects are extraordinary, but the map is the point, and the map keeps growing with every observation cycle, every new deep field, every new spectrum confirmed. What Webb is conducting at the edge of the observable universe is the most ambitious archaeological excavation in human history, and the site keeps turning up artifacts that don't belong. There is something deeply strange about what Webb is actually doing when it observes these early galaxies. It isn't just collecting light from distant objects. It's collecting light that left those objects billions of years ago. And that distinction matters more than it might seem at first. Light travels fast, faster than anything else in the universe. It moves at 186,000 miles per second. At that speed it can circle the Earth 7.5 times in a single second. But the universe is so vast that even at that speed, light takes real, measurable time to cross it. And that means every time you look at something far away, you're not seeing it as it is now. You're seeing it as it was when the light left it. That's not a limitation of our instruments, that's physics. That's the fundamental nature of how observation works across large distances. Start with something close. The Moon is about 239,000 miles from Earth. Light takes roughly 1.3 seconds to cross that distance. So when you look at the Moon on a clear night, you're seeing it as it was 1.3 seconds ago. That gap is trivial. The Moon doesn't change much in a second. But now move further out. The Sun sits about 93 million miles away. Light takes approximately 8 minutes to make that journey. The Sun you see in the sky right now is the Sun as it existed 8 minutes ago. If something catastrophic happened to the Sun at this exact moment, you wouldn't know for 8 minutes. Keep going. The nearest star to our solar system, Proxima Centauri, sits about 4.2 light-years away. The light reaching us from that star tonight left it roughly 4 years ago. The star you're seeing is a 4-year-old image, frozen in the moment the light departed. Now extend that to the Andromeda Galaxy, our nearest large galactic neighbor. It's about 2.5 million light-years away. Every photograph ever taken of Andromeda shows it as it appeared 2.5 million years ago. When that light began traveling toward us, modern humans didn't exist yet. Our ancestors were making stone tools on the plains of Africa. And then there's what Webb is seeing. Month over month, Z14 has a redshift of 14.44. The light we collected from it left the galaxy when the universe was only 280 million years old. That light has been traveling through expanding space for approximately 13.5 billion years before Webb's mirrors caught it. What we're seeing is not month-over-month Z14 as it exists today. We're seeing a 13.5 billion-year-old snapshot of a galaxy that was barely formed. By now, that galaxy has had 13.5 billion years to change. It may have merged with other galaxies. Its stars may have gone through multiple generations. Its structure may be completely unrecognizable compared to what Webb imaged. It may not exist as a discrete object at all anymore. We have absolutely no way of knowing. The light showing us its current state won't arrive here for billions of years. Think about that for a moment. We're studying something in extraordinary detail, running spectroscopic analyses, measuring its mass and brightness, building theories around it. And the object we're studying is essentially a ghost, a record of something that existed 13.5 billion years ago. The real galaxy, whatever it has become, is beyond our reach right now. This is true for every object Webb observes at extreme distances. The deeper it looks, the further back in time it reaches. There's no way around this. Distance and time are locked together. Looking out into space and looking back in time are the same thing. Now consider what sits at the very edge of our observational reach. There's a boundary called the cosmic horizon. It marks the limit of the observable universe, not because space ends there, but because light from beyond that boundary hasn't had enough time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travelling toward us from beyond the horizon set out before the conditions existed to carry it here. Whatever lies on the other side of that boundary, we can't see it. We can't detect it. We can't know anything about it. There could be more galaxies out there, more stars, more structure. Almost certainly there is. But that information is locked away behind a wall of time and distance that no telescope can penetrate. Here's what's strange about the horizon, though. It's not fixed. The universe has been expanding since the Big Bang, and as time passes, light from objects that were previously beyond our reach has had more time to travel. The observable universe is actually growing. More ancient light becomes available to collect as the cosmos ages. Regions that were once beyond the horizon are slowly becoming observable. This means that in principle, the longer we wait, the more of the early universe we'll be able to see. Webb is taking advantage of exactly this. Light from the earliest galaxies, emitted when the universe was only a few 100 million years old, is only now arriving in sufficient quantity for instruments sensitive enough to catch it. The expansion of the universe complicates this picture further. Space itself is stretching. The light travelling from those distant early galaxies is being stretched along with the space it's moving through, shifting to longer wavelengths, sliding from ultraviolet into infrared as it travels. That's redshift, and it's precisely why Webb was designed around infrared detection. The most ancient light in the universe doesn't arrive in visible wavelengths anymore. The universe's expansion has transformed it during transit. Webb is collecting light that has been travelling and changing for over 13 billion years. What Webb is doing then is not simply looking across distance, it's looking across time. Each image it captures is a layer of cosmic history. The deeper the field, the older the layer. And what those layers are revealing consistently is an early universe that doesn't behave the way the models said it would. The galaxies are too bright, too massive, too structured for their age. Every time astronomers push to higher redshifts and earlier epochs, the mismatch between prediction and observation persists. Every photon Webb captures from the edge of the observable universe is a message sent over 13 billion years ago, and the message keeps saying the same thing. We got this wrong. Webb has been operating for only a few years, and already the questions are piling up faster than the answers. Every confirmed galaxy at extreme redshift raises new ones. Every unexpected structure demands explanation. The data keeps arriving, and the gap between what astronomers expected and what they're actually seeing hasn't closed. It's widened. So the question now isn't just what Webb has found, it's what astronomers plan to do about it. The process works in stages. When Webb captures deep field images, astronomers comb through them looking for candidates. A candidate is a source that appears, based on its colors and brightness across different infrared bands, to be extremely distant. These photometric candidates can number in the hundreds from a single deep field. But a candidate is not a confirmation, it's a lead. To confirm a galaxy's distance, you need spectroscopy. You need to turn the telescope toward that specific object and split its light into a spectrum, reading the precise wavelengths it emits. That tells you the redshift. The redshift tells you the distance. The distance tells you the age. Right now, the number of spectroscopically confirmed galaxies at redshifts above 10 is still in the dozens. That's a small sample. It's growing, but it's small. And small samples mean uncertain statistics. You can't rewrite a cosmological model based on a handful of objects. You need a census. That census is being built. Webb is accumulating observation time. More candidates are being flagged. More spectroscopic follow-up is being scheduled. The confirmed sample will grow into the hundreds and eventually into the thousands. When that happens, astronomers will finally have the numbers they need to test models properly. Not just to say these massive early galaxies exist, but to say how common they are, how they're distributed, how their properties cluster. That's when the theoretical pressure becomes truly unavoidable. The theorists aren't waiting around. Modeling teams are already running new simulations, trying to build a version of the early universe that produces what Webb is seeing. Some are exploring dramatically higher star formation efficiencies. In standard models, only a small fraction of available gas in a region actually collapses into stars. The rest gets heated, blown away, disrupted. But if early conditions allowed a much higher fraction of gas to convert into stars, you could build massive galaxies faster. Some simulations are testing this. Others are exploring different feedback mechanisms, the processes by which young stars and black holes regulate their own growth. If those mechanisms work differently in the early universe, galaxies could have assembled more quickly before the feedback. CA shut things down. And some researchers are looking harder at dark matter itself, testing whether its behavior in the very early universe might have been different from what current models assume. Seeding structure faster than expected. Here's the thing about theoretical revision, though. Running a new simulation that fits the Webb data isn't enough on its own. A new model has to do two things simultaneously. It has to explain the Webb observations, and it has to keep explaining everything the standard model already explained correctly. The cosmic microwave background, the large-scale structure of the universe, the abundance of light elements from the Big Bang. You can't fix one problem by breaking 10 others. So the bar for genuine model revision is high. What would actually clear it? Astronomers have a rough answer. If the confirmed population of massive early galaxies grows large enough that no reasonable adjustment to star formation efficiency can account for it, that's significant. If the size discrepancy, the gap between observed stellar masses and theoretical limits, keeps holding up as measurement techniques improve, that matters. If Webb's upcoming observations continue to find galaxies at redshifts above 15 with confirmed spectroscopy, the statistical case becomes harder to dismiss. Webb's extended operational lifetime makes all of this possible on a timescale that's actually meaningful. The telescope was designed for a 10-year mission. The launch trajectory was precise enough that it conserved propellant far beyond the baseline requirement. Current estimates put the potential operational lifetime at 20 years or more. That's an enormous amount of additional observing time. It means the confirmed sample won't just grow modestly, it will grow by orders of magnitude. The difference between dozens of confirmed extreme redshift galaxies and thousands is the difference between an anomaly and a result. Webb isn't working alone. The Atacama Large Millimeter Array, ALMA, observes at radio and millimeter wavelengths, which means it sees things Webb can't. It can trace cold gas and dust in early galaxies. It can measure how fast gas is moving. It can detect the molecular signatures that reveal chemical composition. ALMA has already contributed to some of Webb's biggest findings, including the detection of those galaxy-killing winds. The two observatories are complementary in a precise way. Webb finds the objects. ALMA probes their internal physics. The Nancy Grace Roman Space Telescope is coming. It's designed to survey enormous areas of sky with Webb-like sensitivity. Where Webb looks deep at small patches of sky, Roman will look wide. That's critical for population statistics. You can't measure how common something is from a tiny field. Roman will provide the wide-angle census that Webb's narrow fields can't. The extremely large telescope, currently under construction in Chile, will offer ground-based spectroscopic power at a scale never attempted before. Its mirror spans nearly 40 meters. That's a light-collecting area that dwarfs anything currently operating. It will be able to take spectra of faint early galaxies that even Webb can only barely image. The specific questions driving all of this are well defined. Are the stellar mass estimates for these early galaxies actually correct, or is something systematically off in the way masses are being calculated from infrared photometry? How many blue monsters are there really, and what are they? Are they dense stellar populations, active black holes, or something else entirely? What exactly are the little red dots? When did reionization actually begin, and when was it complete? Was it driven by faint galaxies, bright ones, or both? These aren't vague puzzles. They're specific, testable questions with specific observational paths toward answers. What astronomers don't have right now is certainty. The honest position is one of genuine uncertainty. The data is real. The discrepancies are real. But the sample is still limited. The models are still being revised. And the instruments keep finding things that weren't on any prediction list. The questions aren't narrowing, they're branching. The telescope's job, it turns out, is not to confirm what we know, it's to show us everything we got wrong. Science advances most when observations force it to, not when theories are refined in isolation, not when models are polished to a higher precision, but when the data comes back wrong. That's what's happening right now in cosmology. Webb isn't just delivering surprising results, it's delivering results that don't fit again and again from the deepest reaches of the observable universe. And the question that astronomers are beginning to ask, quietly at first, then more openly, is whether the framework itself needs to change. To be clear about what that would and wouldn't mean, it wouldn't mean the Big Bang didn't happen. The evidence for the Big Bang is overwhelming, written into the cosmic microwave background, into the abundance of hydrogen and helium in the universe, into the observed expansion of space itself. It wouldn't mean that decades of cosmological work were wasted. What it would mean is more specific than that. It would mean that certain assumptions baked into the Lambda-CDM model, assumptions about how dark matter behaves on small scales, about how efficiently stars can form in the earliest galaxies, about the timeline of cosmic structure assembly, those assumptions may be wrong, not everything, not the foundation, but parts of the architecture built on top of it. Think about what happened to Newtonian mechanics in the early 20th century. For more than 200 years, Newton's laws described the motion of planets with extraordinary precision. They predicted the existence of Neptune before anyone had ever seen it. They were the gold standard of scientific achievement. And then astronomers noticed something strange about Mercury. Its orbit didn't quite behave the way Newton's equations said it should. A tiny discrepancy, a small wobble in the path of the innermost planet that nobody could explain. For decades, astronomers tried to fit that anomaly into the existing framework. Maybe there was another planet even closer to the Sun. Maybe the Sun's mass was slightly different than assumed. None of it worked. The anomaly persisted, and it took Albert Einstein's general theory of relativity to finally explain it. A theory that didn't discard Newton's work but revealed it as an approximation, accurate within a certain range and incomplete beyond it. The same process may now be underway in cosmology. Here's what makes paradigm revision difficult. Anomalous observations are not enough on their own. You can always argue that the measurements are uncertain, that the instruments have systematic errors, that the models need only minor tweaks. That argument is reasonable when you have a handful of surprising results. It becomes harder to sustain when the surprises are everywhere, when they span different instruments, different observation strategies, different teams working independently. Webb's findings aren't a single anomaly. They're a pattern. Galaxies too massive too early, too many bright compact objects, reionization driven by sources the model didn't predict, spiral structure appearing where chaos was supposed to reign. A pattern like that demands something more than a minor adjustment to the parameters. But anomalies alone still aren't sufficient to overturn a model. Science doesn't work by falsification alone. What eventually replaces a struggling theory isn't just evidence against the old one. It's a better theory that explains everything the old one did, plus everything the old one couldn't. That's the hard part. Right now, there is no fully formed replacement for Lambda-CDM waiting in the wings. There are modifications being explored, higher star formation efficiencies in the early universe, different assumptions about dark matter behavior at small scales, alternative models of inflation that seed a different early density distribution. Some of these may turn out to be sufficient, small adjustments rather than a wholesale replacement. Others may point toward genuinely new physics. The honest answer is that nobody knows yet. What's not in doubt is the weight of the moment for the people experiencing it. Astronomers working on these observations right now are watching something rare happen. Most scientists spend their careers refining existing knowledge. They fill in details. They improve precision. Occasionally, one generation is present when the map of what we know has to be redrawn. The researchers studying Webb's deep fields may be living through one of those moments. That's not a small thing. There's a reason this matters beyond professional interest. The universe's history, how it went from a featureless hot plasma to hydrogen and helium atoms, to the first stars, to galaxies, to heavy elements, to planets, to chemistry, to life. That sequence is the deepest story cosmology is trying to tell. Every chapter depends on the ones before it. If the early chapters are wrong, if the first stars formed faster than we thought, if the first galaxies grew more massive in less time, if the conditions in the young universe were fundamentally different from what our models assume, then the story of everything that followed is built on a description we haven't got right yet. That's not a reason for despair. It's the reason science exists. The whole enterprise is built around the possibility of being wrong. Built around the principle that the universe doesn't owe us confirmation. We construct the best model we can from the available evidence, we use that model to make predictions, and we build instruments sensitive enough to test those predictions at the edges where uncertainty lives. Webb is that instrument, and it went to the edge and found the unexpected. That is exactly what it was supposed to do. The fact that the results are uncomfortable for existing theory isn't a failure. It's the system working. It's the process generating the kind of pressure that eventually produces better understanding. The universe has never cared about our models, and the James Webb Space Telescope has spent its first few years making sure we remember that. The carbon comprising your body was forged in the core of a star, not metaphorically, not approximately, literally. The carbon atoms in your muscles, your bones, your DNA, they were created inside stars that lived and died billions of years before our sun existed. The same is true for the oxygen you're breathing right now, the nitrogen in your cells, the iron in your blood. None of it existed at the beginning of the universe. The Big Bang produced hydrogen, helium, and almost nothing else. Everything heavier than that had to be built, element by element, inside stellar cores where temperatures and pressures are high enough to force atomic nuclei together. That process is called nucleosynthesis. It is the origin of almost every atom of every complex substance that has ever existed. Think about what that means for a moment. The first generation of stars in the early universe formed from pure hydrogen and helium. They burned through that fuel. The most massive ones lived fast and died violently, detonating as supernovae and scattering their contents across the surrounding gas clouds. Those clouds were now enriched. They contained carbon, oxygen, silicon, iron. The next generation of stars that formed from those clouds was different. They carried heavy elements. Some of them built rocky planets from that material, and after several more generations of stars living and dying, enriching the interstellar medium a little more with each cycle, the conditions finally existed for something like our solar system to form, a star surrounded by a disk of gas and dust loaded with heavy elements, rocky planets condensing from that disk. One of them at just the right distance from the star to allow liquid water on its surface. And eventually, on that planet, chemistry complicated enough to become biology. You are the product of that entire chain, every step of it. Remove any link and you don't exist. Remove the first supernovae and there's no carbon for life to be built from. Remove the second generation of stars and there are no rocky planets. Remove the specific history of our solar system and there's no Earth. It took billions of years and the deaths of countless stars to assemble the raw material for a single human being. Our brains didn't evolve to process that kind of timescale. It's just too vast to feel real. But here's what the Webb discoveries mean for that story. If the early universe was fundamentally different from what the standard model predicted, the timeline of all of this changes. Heavy element enrichment depends on how quickly massive stars formed, how fast they lived and died, how efficiently supernovae scattered their contents. If Webb is correct that the early universe produced massive galaxies far faster than models expected, then the first heavy elements may have been distributed through the cosmos earlier than we thought. The first rocky planets might have been possible sooner. The chain of causation that eventually produced life could have started running earlier than our current picture of cosmic history describes. We don't know yet. That's the honest answer. The spectroscopic data Webb is collecting right now is the first real evidence we've ever had about how the early universe actually worked, rather than how we assumed it worked. The measurements of galaxies like month-over-month Z14 are snapshots of the cosmos when it was only 280 million years old. That's 2% of the universe's current age. The universe at that point shouldn't have been capable of producing bright, massive, structured galaxies. And yet it was. What that means for the sequence of events that eventually produced carbon-based life is still being worked out. Some of the galaxy candidates Webb is identifying show evidence of heavy elements already present. Elements that had to be forged inside stars. Stars that had to form, live out their entire lives, die before the universe was even a few 100 million years old. That's an extraordinary rate of stellar evolution. It suggests the first generation of stars burned fast, died violently, seeded the surrounding gas with complex elements far sooner than our models assumed. The cosmic clock that ticks from the first stars to the first heavy elements to the first rocky planets may have been running faster than we thought. You are sitting at the far end of that timeline, made of atoms that have cycled through multiple stars, travelled across galactic distances, spent billions of years drifting through space before gravitational collapse, solar system formation, planetary chemistry. Biological evolution assembled them into something capable of watching a video about where they came from. The carbon in your body and the carbon in a distant galaxy observed by Webb are made by the same process. The iron in your blood and the iron scattered by a supernova 13 billion years ago are the same element produced by the same nuclear reactions. There is no meaningful distinction between the stuff the universe is made of and the stuff you are made of. Webb is collecting light from month-over-month Z14 right now. That light left the galaxy 13.5 billion years ago, before our sun existed, before Earth existed, before any of the stars whose deaths produced the atoms in your body had even formed. It travelled across an expanding universe for 13.5 billion years and landed on a mirror the size of a dining room table orbiting the Sunday 1.5 million kilometres from Earth. And what it's telling us doesn't match what we expected. The early universe was brighter, more massive, more structured, more active than the models said it should have been. And if that's true, then the story of how the universe went from a hot hydrogen gas to beings capable of asking where they came from is a different story than the one we've been telling. The story of where you came from is written in that ancient light, and the James Webb Space Telescope is still reading it, one galaxy at a time, finding that the story is stranger and older and more surprising than anyone had the courage to predict.